É. Som? Testando. Reduziu o volume um pouco. Testando. Aumenta um pouquinho. Testando. Testando. Som. Tá bom assim? Pessoal do fundo ouve? Beleza, né? Beleza. É. Okay, switching to English now. So, it is, I'm Arthur Moraes, by the way. I'm working at CBPF. And for those of you who are attending the conference, well, welcome to Rio de Janeiro. Welcome to CBPF. We've been very fortunate with the conference organizers that this time around we were allowed to do a joint session between the regular CBPF Colóquio and the conference. So today we're very pleased actually they're receiving such a renowned guest that's going to be speaking to us about Rattle and shine by compact binary mergers in the era of gravitational wave astronomy. So our speaker today is Professor Lehner. He is currently at the Perimeter Institute for Theoretical Physics in Canada. And just to tell a little bit about his scientific career so far, he got his PhD from the University of Pennsylvania, and then he held postdoctoral research positions at Texas, and then at British Columbia. We were just chatting about that because I worked for a while in Vancouver as well. Lovely place, lovely part of the world. And he also worked as associate professor at LSU, Louisiana State University, and then at Guelph, already in Canada, and then joined the Perimeter Institute for Theoretical Physics, where he now holds a position of senior researcher. He is also, he's been awarded several awards for his contributions to the research in gravitational waves and in all that study. I'm not going to list all of them because they are quite comprehensive list here on the Colóquio advertisement. And it's a great pleasure for us actually to receive him and to hear about this, which has been a hot topic that we just found out this year that people detect these gravitational waves. And I hope you can have a great nice time with our talk. And I'll pass it on to you now. So welcome and thank you very much.
Thank you for that totally undeserving introduction. So it's a great pleasure to be here. Thanks for the organizers both of the conference and the CBPF. It's my first time back in Rio in the past 30 years. So this morning coming from the airport here, I thought it was going to take another 30 years to get to the institute. Okay, so that's the first bad joke. So I'll have a few. So first, let me just, as you know, in February, there was this discovery, and we're going to be talking about this in the context of what's coming, and not so much about what happened in the past, but what the challenges are for the future and trying to realize what the potential of gravitational waves has always been kind of broadcasted or promised to be. And just to highlight that in many respects, we still have a lot of ways to go. But just to put it in context first, let me just go a little bit back in time. This is a quote from Richard Feynman, who went to this conference in 1962, and it was a general relativity conference. And as you can tell, he was not very pleased with the status of the field. He wrote, I think this is to either a friend or his wife, I basically say, remind me never to come back, because there is nothing going on in this field. Of course, as every bright scientist will always have a route to escape. He also wrote this book, and of course, in hindsight, he can always say, well, given what we know now, I was just joking. So this what happened 53 years after he wrote that, or about 100 years after Einstein wrote down the Einstein equation of motion. The top, is there a pointer? Maybe this one. So the top panel is what the detectors in the US, which is called LIGO, detected in February 14 of last year. Just to put this in perspective, LIGO was supposed to not be measuring at that time. This was a transition stage from the engineering run, where they just were trying to make sure the detector was working as it was supposed to. And 3 days later, the real scientific mission was supposed to start, and they saw that. The first reaction of people first also I should say, I'm not a member of the collaboration. I was a member till a few years ago. When I moved to Canada, I stopped being, but of course I'm very much involved, very closely discussing with people in the collaboration, because some of the work I do is to provide theoretical information for their analysis. But if you talk to people that were actively involved in the detection, they will tell you the first thing they thought when they saw that was, oh, these idiots screwed up. LIGO has this series of internal benchmarks or internal tests to ensure that what they've seen is the true gravitational wave. As opposed to, say, an experiment in particle physics, where you can turn off the source and then check what the background noise is at the detector, LIGO cannot do that. So one of the many things they do is to directly inject gravitational waves by hand, either by forcefully moving the mirrors, as a gravitational wave would do, or by sneaking in data in the data stream and having people analyze without telling them. And then eventually, once they pick it up, they said, okay, we seem to have a gravitational wave. They go and check if that was one of these so-called blind injections. And if it wasn't, then you could tell maybe this was a real gravitational wave. The problem with this signal, or the problem between quotes, is that it was so loud that you could see it. Typically, and I'll show you in a few slides what the detector's noise looked like. Typically, the thought process was that the signal was going to be buried in the noise and you have to dig it up. This one, they just saw it. So that was the first thing. Then they realized that, oh no, we're in the scientific, in the engineering realm. We're not yet ready to actually inject any fake signal. So this is either real, either some vibration that caused things to look this way, or someone hacked us and maliciously put a signal in our data. And they went through all possible tests to very nervous days till they convinced themselves that this is indeed a gravitational wave. It has some weird characteristics, perhaps not necessarily expected, which is this very high signal to noise. And once you deconvolve and try to obtain the parameters of the source, and this we'll discuss in a minute, they realize that the masses involved were so large that it was the reason why the signal was so strong. Anyway, so let's go by parts, and then we're going to be trying to dig out a few things from here and actually try to think what happens towards the future. So the implications of this signal itself, as I said, we're going to go through in more detail. There are many. One of them, of course, the most obvious one, is that gravitational waves exist and we can detect them. This doesn't yet necessarily imply that Einstein was correct, as many people or the press wanted to say. This just says that the perturbations in the space-time move at some speed, and yes, it is consistent with general relativity, but we don't know yet. We're going to try to explore that question a bit more. The signal, now if you assume the general relativity is correct, the signal is completely consistent with the existence of black holes in binaries. And importantly, these black holes in binary happen to have masses that are quite large, that are of the order of 30 solar masses. If you go back in the past and try to check what models out there were predicting for the masses of the black hole, people will definitely point to specific papers where they have written a model where such a mass, where such a binary mass was predicted. But this is among many, many predictions. The population synthesis models predict a whole vast range of parameters, of possibilities. And if you actually ask before the detection, how much money were people willing to put for such a binary, I don't think you would have gotten many takers. But this was all in the context of a promise. This is a promise that was delivered or was given to the National Science Foundation in the early 90s to get quite a bit interesting amount of money. Initially, it was of the order of a few $100 million. Today, if you iterate all the amount of money from the beginning to the detection, it's of the order of $1,000 million. The promises that were put in paper to try to get the proposal to go through is a list of basically these points. One of the things you could do if you have LIGO was to test it where gravity was described as in general relativity. And in particular, you were able to test the theory many orders of magnitude beyond any existing test that was available at that time, or even today. You could tell because the primary sources for gravitational waves are compact binaries. These are binaries that are formed by either black holes or even stars. You could test the populations of these objects. In particular, binary black holes, we don't have and now there is a question mark. We don't have any other way of seeing what the signal from binary black holes if we don't concentrate on gravitational waves, because we do not think generically binary black holes of stellar mass ranges are able to produce electromagnetic counterparts. So we're going to come back to this point in a second. And we wanted to know what type of binaries are there and where they are. We also, or in paper, also was the possibility to test the equation of state of neutron stars and understand the behavior of cold nuclear matter. We kind of know how nuclear matter behaves when it's very hot, because unfortunately people have been playing around with nuclear weapons and things of the sort, but not about what happens when the matter is in such a high density but cold. And of course, a lot more physics and astrophysics. In particular, one beacon has always been to try to understand better this possible connection between gamma ray bursts and compact binaries that are colliding. And of course, surprises. Every time you open a new window to the universe, we have found new things. And of course, everyone is eagerly awaiting what the surprises might be. And in some respects, already the binary masses involved in this event were a bit of a surprise. So that's the total order of these promises. So let me just tell you what is in store to try to go after the signals. So far, what is an operation is LIGO, Hanford, and Livingstone. There is another one, the Italian and French collaboration called Virgo. That's one that has always been in that kind of parallel development with the LIGO observatories. But that one, in this stage, has been lagging behind a little bit. Supposedly, it was planned to join in a mission that starts this year in August, but they have been having some problems with the suspension mechanisms of the individual mirrors, that there are going to be delays, and so now people are hoping that by the end of the year that it will join, if not, maybe earlier in the next year. The importance of having more than 2 detectors is that LIGO, or this is the gravitational wave detectors, can only do sky localization by triangulation. So basically, just by checking the time of flight between the different detections, then you can pinpoint the location of the sky. That pinpointing of the sky localization is not great by astrophysical standards, but it's actually pretty decent given that the field is just starting. And so what I have here is a table that is has been always a workhorse table of the LIGO collaboration, or the LIGO scientific Virgo collaboration, LIGO Virgo scientific collaboration. Because, as we'll discuss, these detectors were always built having in mind binary neutron stars. They were never built having in mind binary black holes. Binary black holes were something you could see, but of course, so the science foundation would not give you or give people money for a detector for the event that may be detected. In the case of binary neutron stars, we knew that the galaxy has about a handful of binary neutron star systems that will merge within the Hubble time. And because of that, the design of the detectors was carried out in a very particular way, which is what we'll discuss, which has implications on what is that has been observed from the signal. But this gives you more or less a timeline of what the number of sources will be with respect to binary neutron stars. So by the 2015, the number of detections is between 4, 10 to the minus 4, and 3. That huge range is a manifestation of the ambiguities and the poor knowledge that people have as far as the population synthesis of how you actually come up with these binaries. Of course, then detection will actually then allow to converge on a particular model that will be consistent with the observation. And as time goes by, more detectors get added in, and the sensitivity of detectors is improved, you eventually will be able to localize systems in the sky with, say, a 5 square degree window, that's 17% of the binary stars, or 50% within the 20 square degree window. That's not very small. It's a huge chunk in the sky. But also given that LIGO can only see so far, and you see this in the column that says range, for binary neutron stars, it is expected that the range, how far LIGO can see binary neutron star system, is of the order of 200 megaparsecs or 130, depending on what particular configurations and detectors join in. Eventually, there is also one going to be in India. So it's a sister detector to the one in the US that is actually being moved to India. And interestingly, when the discussions were being conducted to perhaps move one of the 3 detectors that initially were going to be in the US, 2 in Hanford and 1 in LIGO, it was realized that having 1 detector elsewhere was actually very important. Australia came through saying we want to host it, but then given that they are also hosting the SKA, that's too much money for a single country to try to afford. When Australia falls down, there was actually a movement between Argentina and Brazil to try to say we can probably step up. Because LIGO was going to give all the equipment for free, quote unquote, and the host country had to come up with an interesting number of about $150 million, which is what costs to build the facilities, construct the tubes, etc. And much of the money goes into actually creating vacuum. And Japan is extremely aggressively constructing an interferometer in the Kamiyako mine. This is a 3-kilometer interferometer, and as far as I know, very recently they achieved locking for the first time. The sensitivity is still very bad, but they are extremely fastly progressing from not having anything 2 years ago or 3 years ago to actually having a detector already on the ground and beginning to improve sensitivity as they go along. Of course, this is in the context of a much larger effort. So the picture on the top left corner, that's the LIGO observatory in Louisiana. On your right, you have a similar concept, but now cheating, having nature provide the laser beams for you, you actually use pulsars. And by measuring for many, many years or decades, the time of arrival of pulsars that are extremely sharply constant, whenever there is a delay, then that might signify a gravitational wave. Of course, they have to fight with, for instance, interaction of the beams as they go through the ISM and Regis turbulence on the Earth atmosphere, etc. This is why there is a lot of statistics going on. But these guys are also getting enough statistics that maybe in a few years we'll be able to come out and say we're also detecting gravitational waves. And there is the concept of LISA, and sometimes, depending on what you see, it's called ELISA or it's called LISA. And this is an array interferometer that would fly in space. Now, instead of having 4-kilometer arms, it has arms of the order of 1 million kilometers. And how many millions depend on how many millions the US is willing to put in the mix, because it's primarily a European mission, which if it has some non-trivial amount of contribution from the US, will be LISA, otherwise it would be ELISA. This is scheduled to launch in 2034, but that's a schedule that was set up prior to the detection. So everyone expects that this will be pushed to an earlier date, and maybe it could be as early as 2028, 2029. The gravitational wave spectrum, I mean, we are familiar with just looking at the sky with telescopes. So we know, say, optical, infrared, X-ray, radio, they all cover different windows. So the similar story goes on for gravitational waves. LIGO is sitting at around 100 hertz. So it goes from about 10 hertz to a kilohertz or 2. That's the sensitivity. The frequency of gravitational waves typically goes like 1 over the total mass of the system. So the least massive a system is, the higher you go to frequencies. And then if you consider sources that will be catchable or detectable by LISA, then you're in the order of 10 to the minus 4 hertz. Supermassive black holes, starting with the pulsar timing arrays, are in the nanohertz. And from a completely different point of view, people are looking at the effect of primordial gravitational waves on the CMB. And of course, we know there was a claim a few years ago that went away, but still people are very actively going after the R modes. So how do you go after trying to detect these signals? As I said, prior to this detection, the understanding was that if you look at the top right plot there, that's a plot of sensitivity versus frequency. So you can tell that it goes from about 10 hertz to a kilohertz. And the different colors demark the sensitivity that a detector would have at different times. So the detector, the reach to the full design sensitivity It's always intertwined between some science mission with some intermediate value of sensitivity, then some more upgrades and so on. So LIGO is undergoing some upgrades now to have better sensitivity than the one that was used for its detection. So if you were to picture a binary star going through that, it actually typically, unless it's very close, will have a signal that goes from left to right. As this binary gets tighter and tighter, the individual objects are going faster and faster around each other, the gravitational waves go higher in frequency. But the signal will go under the noise curve, typically. And you need to dig it out by data analysis. And the workhorse data analysis, the best thing you can do is to do a convolution of the data that your detector is taking with a prior knowledge of what the signal looks like. And that's called match filtering. So you basically construct an inner product that is weighted, of course, by the noise of your detector. And from there, you get both the ability to pick up the signal from the noise, and then whichever is the best template that agrees with, but maximizes the inner product, will be the one you assign the most likely candidate for giving you the physical parameters of the source. But as I said, this signal was extremely loud, so there are other options you can do. Some is just to look at the excess power in the different detectors and do cross correlation. So then you just go, if there, on each individual detector, you see you're computing, if you want, just the strength of your data, of the data coming off the detector, and see if at any point you have more power as opposed to some time before or some time after. And then you do a cross correlation with the two detectors, and then you can dig these things out. And this is this plot here. It's just plotting excess power. And if you combine with what the other detector is seeing, you see that at about the same time, shifted in time by some amount that is consistent with a signal that propagates at the speed of light in between the two detectors. The one in the middle also does something else, which is, suppose I don't know anything about the signal, what the characteristics of the signal is, but let me just use some reasonable bases. And in this particular case, have been chosen wavelet bases, which are essentially Fourier moments multiplied by an exponential. And then you just go window by window to see if the convolution of that with the detector's data actually picks up something. And in the middle plot here, what you see is both, well, you can see three lines barely, but one is the line you pick up with the template. The other one is the line you pick up with this wavelet decomposition. And this last jagged noisy feature right here above this color panel, it is the result of taking the theoretical model, either through the template or through this wavelet, subtracting it from the source, from the data stream, and seeing what is left. So you go from something that has a very clear pattern to something that essentially looks like noise. So that's another indication that you have extracted something that was real there. And whatever ends up being as a remainder doesn't really have much structure. And these two other plots, I'm not going to go into this, but this is just a measure of how confident the detection has been. And depending on where you use the template base or the wavelet base, you either say you have over 5 sigma confidence of my result, that's a right plot, or over 4.6 sigma confidence of the wavelets having picked up something that was real in the signal. So, but I said beyond the detection, the most interesting thing, we wouldn't be worthwhile spending $1 billion to at the end of the day say, well, we know we can detect gravitational waves. What we wanted to do was physics all along. So, as I said, the main venue to try to get physics out of the signal is use these match filtering techniques. For binary, so then you have to ask, well, how do I get this theoretical information? So we have very strong consistency support for general relativity being the theory that describes, well, binary systems when they are sufficiently far apart. And there is a Nobel Prize for the pulsar in 1913, class 16 for Pauls and Taylor, that is showing that general relativity, at least in the highly separated regime, does an extremely good job. So we have a good confidence that the binary dynamics described by, say, a post-Newtonian analysis, which basically just rewrites the equations of motions of these objects as if it were Newtonian, dominated by Newtonian mechanics, plus some correcting terms that basically measure the departure of the velocities being very low and masses being very, the mass ratios or densities being very weak. As time goes by, however, these objects will get so close that nonlinearities of whatever theory, maybe general relativity or whatever other theory, should kick in, should dominate, and then we need to try to get templates or the knowledge for trying to dig these things out. And one particular striking feature of this particular detection is that if you actually ask the question, how much of the binary, of this very nonlinear regime of the binary is in the signal, is essentially everything. The signal or the bodies, the masses of the binaries are so high. Remember I told you that the frequency goes like inversely proportional to the mass. So this is a very high mass. It pushes it pushes where the binary is to the left side of this plot. As a result, actually you're only seeing the merger. You did not see the early part of the binary. And that elucidates, or actually puts in perspective, the fact that we were not very ready to actually ask the right questions in this very nonlinear regime. I'll tell you why. The reason is we have perfectly good templates, and I'll show you some examples of what happens in general relativity in this very nonlinear regime. We can do it, and this is what the detection has used. But we have no other alternative theory of gravity, with one exception, where this similar work is done. So we really do not know, when we do this test of let's try to compare the data with general relativity or whatever else to see which one does a better match, we don't have the whatever else. We just have general relativity. And of course, if you look in the signal for something that looks like general relativity, you're going to get general relativity. So the test, while it's pretty compelling, the general relativity seems very consistent with the story, we haven't put the signal to the best test possible. After merger, so let me just go to the different piece of the signal. So now we said we are living in the nonlinear regime. So we have the pre-merger signal. Then here is more or less where the merger takes place, and then you have an object that decays and goes to quiescence very rapidly. So general relativity has no problem describing that. We know two black holes come together, form a highly distorted black hole, which quasi-normally radiates itself away to go back to Kerr. All that picture is fine. But it would be entertaining, at the very least academically, to think what else could do something like this. So one example is to try to do it phenomenologically. Is to say, well, I have an object here that decays very rapidly to something that doesn't radiate anymore. So one option that people have pursued is to think of, well, suppose this is an object that maybe is strange, we don't know its properties, but we can phenomenologically try to understand it in terms of something that loses energy. And every time we say have a system that loses energy, we think of viscosity. So there are models out there that try to understand this decay rate in terms of some object that has some particular strength of shear viscosity and some particular strength of bulk viscosity. When you put these numbers together and try to extract how rapidly these would be, it just means that the viscosities are so high that we do not know, or we cannot yet think, of any particular system that will be consistent with that signal. So that's just as one example of what it said. We, in some sense, the community was caught slightly unprepared to deal with the binary, very complicated binary merger, because all along people have been thinking that the main source was going to be binary to stars, which would traverse the whole LIGO sensitivity curve, and the merger would happen beyond what LIGO can see. So this is just one example that I'm a classic. So these are the first simulations that people did. This is actually from my colleague and friend Franz Pretorius. The very first time someone got the binary black hole simulations under control was Franz in the year 2005. And this is more or less what you get. Oops. For the binary, so you have these objects going around each other. There is a little bit of eccentricity because of the initial data. Eventually, these two objects will come merge into a single one, and very quickly, it will just look like a very quiescent object.